Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement the remaining parts of the polynomial transformation. First, we start by generating nonlinear training examples where the input feature x1 and the label y are related through a nonlinear relationship. Specifically, the label y in this case is related to x1 through the sine function. So we calculate y as sine of 2 pi x1 plus noise. So we implement the data generation process through two functions. The nonlinear function actually performs a nonlinear transformation of the input feature x to generate the output label y. So we first sample the feature x1 randomly between 0 to 1 with desired number of samples. Then we apply the nonlinear function on the input and add a random noise to it. So we add a Gaussian noise with a specified standard deviation, and we get the value of y as the nonlinear function of x plus some noise, and here the nonlinear function is sine of 2 pi x1. Next, we implement a couple of visualizations, one for the training data itself and second is for the model fitment. And remember, we can do it because we just have a data set, a toy data set with a single feature x1. So we can set the number of samples required and control noise added to the example through std parameter. Let's look at the 10 samples that are generated with std parameter of 0.2. You can see that this is the training data that is generated, which is denoted by these blue circles, and the red one and the green line that you see over here denotes the actual function, the sine 2 pi x function. And since we add noise, the blue points over here are slightly dislocated from the actual function, and this particular dislocation is determined by the parameter std, which is set to 0.2. If we modify this parameter, let's say modify it to 0.01, and we can rerun this, you can see that points are pretty much on the line, right? So if we further reduce it, the points will be are perfectly on the function, because we add a very small noise, because the noise is controlled by noise is generated from a random Gaussian distribution with this particular standard deviation parameter. On the other hand, if we increase it, let's say to 1, you can see that points are far away. Some points are really far away from the actual function that was used to generate the points. So if you make it 10, the points are even further away. So we'll set it to 0.2 for our exploration. We'll generate 10 points from this. So these are examples that we have generated, which are denoted by the blue dot, and the green one, the green line, the smooth green line that you see is the function that was used to generate these examples. So we take the feature x1, which was uniformly randomly sampled, then we apply the function which is shown in the green, add some noise to get the label y. Now that we have generated the training data, let's apply polynomial regression model to model the relationship between input and output. And remember that polynomial regression is nothing but polynomial transformation plus linear regression. So what we do is we first fix the degree of polynomial transformation, apply the polynomial transformation of the specific degree to the input feature matrix, and then we apply the linear regression on this particular transform feature set. So we perform linear regression dot fit with input as x underscore transform, the transform feature set, and the label y. And finally, we visualize the model fit. So let's change the degree. So the one that you see on the screen right now is the degree 9 polynomial that was used to generate that was used to learn the relationship between input and output. If we change it to some different degrees, you will see different fitment. Here in case of degree 9, you can see that the uh, the 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 model, the learned model, which is shown with the red line, is perfectly fitting the training set because it passes through each and every training point. Let's try a lower degree polynomial model. Let's say degree 2 polynomial model. You can see that degree 2 polynomial model doesn't fit the training data that well. We can try other degrees. Let's say degree 3 polynomial. Yeah, this looks like a reasonable fit. It is not perfectly fitting the training data, but it is not too far away from the actual values of y. So you can see that the error across different points is much lower than the second degree polynomial or second order polynomial. If you make it 7, for example, now you can see that this particular shape is not that smooth, right? If you compare it against 3, if I change it to 3, you can see that the model, which is the red curve, is pretty smooth as compared to, let's say, something like 7, where it is not that smooth as compared to 3, right? So this is how you can try polynomial models of different degrees. So again, it is very simple. We apply first polynomial transformation of the desired degree or of the desired order and apply the linear regression to learn the relationship between the input and the output. Now we actually, experimented with a few degrees. We changed degrees over here and examined the fitment. Let's look at this in the single frame. So here what we have done is we have used different polynomials of different degrees 0, 1, 3, 5, 7 and 9, and then essentially perform polynomial transformation of each degrees and apply linear regression to learn the relationship between input and the output, and we finally visualize the model fitment. So you can see all 6 models on the screen. You can see that for m equal to 0 or degree equal to 0, we have a model which is a straight line passing through 0. For degree equal to 1, we have another line. So this is a classical linear model. Then degree 3, we have a smooth fitment of the model. Degree 5 also seems to be resembling to degree 3, has also very smooth fitment, but degree 7 onwards there is some wiggliness in the trained model, and degree 9 model literally connects each and every point in the training set. So degree 7 and degree 9 seems to be overfitting because they produce very close to 0 training error, but we are not sure for for a given test set how they will perform. So another observation to be made here is, as we increase the degree of the polynomial, uh, the the model becomes more and more complex. It is not as smooth as compared to the lower order polynomial functions. So as you can see, as we vary the degree of the polynomial, we get one model per degree. So here we have 6 models for 6 different degrees that we tried. Now which model is the best model? So we have a problem of model selection at hand. We need to choose a single model from these 6 models. And let's look at the procedure for model selection. So here we'll first fix the list of degrees that we want to experiment with. Just like this example where we fixed 6 degrees that we want to experiment with. So we have to first fix the degrees that we want to experiment with. Then we'll divide the training data into training, validation and test. For each degree m, we'll train a polynomial model with the training data, and this polynomial model uses polynomial transformation of degree m, and then we calculate training and validation errors on trained model. For the error measures, we can use either root mean squared error or the loss as the measure of errors, and we calculate those errors on training and validation sets. And finally, we select the model with the lowest training and validation error across among all models. Again, there are a couple of helper functions for plotting the model selection, and another one is to convert the dictionary to data frame. This will be used for looking at the weights that are obtained from polynomial regression of different degrees. So the implementation is quite straightforward. We first fixed a list of degrees. So you want to experiment with each degree from 0 to 10, and then we first perform the polynomial transformation of the desired degree and then apply linear regression in order to learn the relationship between input and the output. We copy the weights of the linear regression model in the weights dictionary with the corresponding degree, and we also append the training error and validation errors to the lists. And finally, we plot the training error and validation error. We have training error in blue and validation error in red. And you can see that as we increase the degree of the polynomial, the training error and validation error both start decreasing. After a point, the training error continues to decrease further, but the validation error, instead of decreasing, goes up or increases from that point onwards. So what does these left hand side models indicate? Here the training error and validation error are high. So that means the models are underfitting. Let's look at the model underfitting phenomenon. So you can see that for model with polynomial degree 0 and 1, they are pretty much underfitting. They are not able to learn the relationship between training, the training data between the features and the labels. So you can see that there is a there are large errors at each training point for this particular linear model. As you can see here, whenever we try polynomial regression with lower degree polynomial transformation, we have high training and validation errors. This points to potential problem of underfitting. On the other hand, if you look at around this region, you can see that over here First, the training and validation error went down, but after a point, the training error continued to drop, but validation error starts rising up. And this points to the problem of overfitting. So if we use higher degree polynomial functions, we run into the risk of overfitting. So let us look at the weight vectors for these different models. So on the columns, we have polynomial models of different degrees. So this is a weight vector corresponding to polynomial model of degree 0. This is a weight vector corresponding to polynomial model of degree 1, degree 2, degree 3, all the way up to degree 9. So we try models up to degree 9. And you can see on the rows we have weights for each of these features, each of the transform features. So this is the zeroth order feature, first order feature, then the second order feature, third order feature, all the way up to ninth order feature. Remember, we have a single feature over here. So this is 1, x1 squared, x1 cube, x1 raised to 4, x1 raised to 5, all the way up to x1 raised to 9. So these are the weights for each of these transformed features. So you can see that the zeroth order feature has all small values or all small weights, but as you and you can see that here the weights are 0 because those features do not exist. In the zeroth order model we just have a single feature. In the first order model we have zeroth order feature and a first order feature which is a feature itself. In the second order polynomial model we just have 3 features, so rest others are 0, so you have to just ignore them. And as we go towards the right, for example, this is the polynomial model of degree 9 and you have all 9 orders or all 9 degrees present in that model. That's why we have a feature vector, we have a weight vector of size 9 for polynomial model of degree 9. In case of degree 8, we have weight vector containing 8 values. Here we have 7 values. Got it? And as you can see, the zeroth order, first order and second order polynomial model have all small weights. But as we go from the third degree model onwards, certain weight starts shooting up. Here the weights are far higher than compared to these weights. And as we go towards higher order polynomial, the weights have blown up quite drastically, quite dramatically. You can see that here the weight is something like 378k, which is a very high weight assigned to let's say 6th order feature. So you can see that as we increase the degree of the polynomial, we tend to get models that overfit. And the way they overfit is by assigning large weights, large value to different weights. And this is a problem. These large weights are mainly problematic because if we make a small change in the input, it causes a large change in the output. And this phenomenon is called as high variance problem or overfitting problem. In order to illustrate this problem, let's take an example model where y, the label, is obtained as minus 0.53 plus 185x1 plus 894x1 squared plus 3250 x1 cube. Let's use let's change the value of x1 from 1 to 2 and calculate the y values. So for the value of x1 equal to 1, if we substitute this value in this equation, we get the output of 4328.47, and if we change it to 2, the output shots up to 29,945.47. So you can see that even for a small change in the input, we get a large change in the output, and this is not desirable. This simply points towards non-smoothness of the function. The function wiggles too much, and because of that we get a very large change in the output for a corresponding small change in the input. We can fix this overfitting problem in two ways. One is by bringing in more data, and second is by using the regularization. We'll study regularization in the next collab. We'll implement regularization in the next collab, but in this collab we can try to fix the overfitting problem by bringing in more data.